Welcome to Micro Communication course. We continue our discussion from the Microstrip line here. As we have seen earlier, a characteristic impedance of a line, that microstrip line, it is depending upon that the effective value of a dielectric constant, natural logarithm 8h by W plus W by 4h, and this equation valid when we have WH is less than 1. Now another equation we have seen that Z is equal to, we say that 376.7 under root of epsilon effective H by W. This equation is valid when we have a W by H is very greater than 1. So now what will be the effective value of this dielectric constant? The effective dielectric constant, if you see that for a given particular line, so it is depending upon that a field distribution. How that lines are distributed here in the substrate as well as the line is are distributed in the air here. So based on that, we can calculate that the effective dielectric constant. But this dielectric constant, that is depending upon what will be the width and height of the strip line as well as the epsilon r value. Okay. So now what will be the effective value? The effective value of a dielectric constant epsilon effective is equal to, depending upon that epsilon r of a material by 1 plus 1 by 2 plus epsilon r minus 1 by 2 here in bracket 1 plus 12h by w raised to minus 1 by 2 plus 0.041 minus w by h bracket square, and this equation is valid when we have the w by h ratio is less than 1, less than or equal to 1. Or we write another equation, because we have the two characteristic impedance when we have W by H ratio is less than 1 and W by H greater than 1. So according to that, that effective value of a dielectric constant or effective dielectric constant, it is depending upon that W by H ratio. Okay, so again we rewrite here W by effective here value epsilon r plus 1 by 2 plus epsilon r minus 1 by 2 in bracket 1 plus 12h divided by w raised to minus 1 by 2. And this equation valid when we say that a w by h ratio is greater than 1. Okay, this one is greater than 1. Now this above equation is valid when we have a w by h ratio is less than 1. And this epsilon effect is depending upon that what will be the sub material we are using. And that for a given particular material, it has a relative dielectric constant of the substrate material. For a given particular line, we say that the effective dielectric constant can also be right in terms of a dielectric constant. Okay, so we say that epsilon effective for a given particular line can be right in terms of a relative dielectric constant of the substrate there. We can write here 0.475 epsilon r plus 0.67. This one is about the effective dielectric constant of a microstrip line, and that effective constant that is related to the epsilon r value, not with respect to that w and h for the strip line there. And the phase velocity of the waves propagating through this line, it is depending upon that Vp is equal to C by epsilon effective. Okay, C by under root of epsilon effective. And we say that wave is propagating through the line. Okay, wave is propagating through the line. That wave is what? What is the mode of the wave? That is about a quasi TM mode. It is propagating through the strip line, microstrip line. So in that case, for this quasi TM mode of propagation, so it has some guide wavelength, and that guide wavelength lambda g, it is depending upon the constant value lambda 0 here. Okay, that is about a that is the cutoff value here for the TM wave here, and a effective value of a dielectric constant. Okay, so means this one is a function of what? What we can say here? Guide wavelength is depending upon that epsilon effective. But we say earlier that the effective value is depending upon that epsilon r plus w by h here. Okay, w by h. As well as that effective value, we say they is depending upon that what will be the phase value here. It will it will use to find out the guide wavelength. Okay, so all the factors are depending upon the what will be the impedance. This effective value, that's about the line impedance here, characteristic impedance. We say we need to know about what will be the effective value, what will be the h by w ratio or w by h ratio. Okay, likewise. So all the factors, okay, they are dependent on the each other. Then what are the losses? Okay, so we talk about the losses in the microstrip line. So generally the losses depending upon that what material. Okay, earlier we say that they have a substrate material, and substrate material it has a epsilon r value, and we have a strip we are using, and that strip is nothing but even conducting strip, and that conducting strip it has some particular width as well as it has particular thickness. So then that losses are depending upon the what will be the strip width and what will be the thickness there. If the strip width is smaller there, then what happen? Then there will be a fringing effect. Okay, so that's why we need to talk about that. That strip width should not be a smaller here. And again, when we are designing or developing that strip line with a small width, then it is difficult to process that strip line with a small width there. And again, that strip width increases here. So then again, what happens? The frequency it has some particular limitation on the operating frequency. So generally, we say that a microstrip line that is used for the a given operating frequencies, but it has characteristic impedance that will be a very small, or we can say that that line is a low impedance line. Okay, that microstrip line is nothing but a low impedance line. So that's why that losses in the strip line or a microstrip line, because it has a conductor, so that's why it has a conductor losses. Okay, then what we can say that we are using a strip there, and that strip will be a small or a large. Okay, then according to the width of that particular strip, so it has some particular resistance. Okay, so then we again that conductor losses that are depending upon that what will be the size, width. Okay, so what will be the metallic material or metallic structures that we are using. Based on that, a conducting losses are there. Then a dielectric loss. And then now this particular dielectric losses, it is depending upon that what type of a substrate we are using. Okay, this what we say that epsilon R. This one is depending upon that what will be the conductivity. It is related to the conductor size. It is related to the strip here. And then dielectric losses. Then what particular material we are going to use here, so that okay, so that that losses will be minimum. For attenuation, whatever the signal is propagating, that is attenuated based on this conducting loss as well as the dielectric loss. So we see first one by one what will be the conductivity of this particular substrate material. Okay, that dielectric constant, because every material it has a different conductivity. So that's why the losses are depending upon that what will be the conductivity of the substrate there. Okay, that substrate material. So we say that earlier conducting factor perfect dielectric, imperfect dielectric. Perfect dielectric conductivity 0. If it is the imperfect dielectric, then it has a some value of a conductivity there. Okay, imperfect dielectric. So conductivity is not equal to 0. Okay, conductivity is not if it is a imperfect dielectric. So, but if it is a perfect one, so in that case, a conductivity will be 0. So that's why we say that for a given particular material, what will be the epsilon r there for a given particular material, and what will be the conductivity of a given particular material. So this factor for a given particular material we defined earlier, that is about a tan delta, and then this tan delta will tell you what will be the losses of a given particular material. Okay. Then another type of a loss in a strip line, that is about a irradiation loss, and that irradiation loss, if you see here for a given particular material, then again it depends upon that is substrate there. So what substrate material we have? Okay, because some material support a higher frequency, some material support for the lower frequency. Then that loss is again depending upon that what operating frequencies we are using. Okay, so that's why these are the main losses in a strip line there. So we say that a conducting losses, that is we can write here alpha D for the conducting losses, dielectric losses we say that it is depending upon the dielectric constant. Okay, that's why we can so conducting losses alpha C. Okay, this one is about a dielectric constant, and this one is about depending upon that irradiation losses alpha R here. So we talk about all the losses here, and what are the values, and how to obtain these losses there. That we need to be learned here. But we need to know about how to minimize this particular loss. Okay. So to minimize the losses, we need to consider that strip thickness, okay, whatever the for a given microstrip line, this one is about a strip. Strip it has some particular width here, strip it has some particular thickness. So if you consider that the strip thickness, if it is larger than the skin depth, okay, is the skin that thickness is if it is larger than the skin depth, then that losses will be minimized there. So that what is skin depth, again it is depending upon the if operating frequency. Okay, at that particular operating frequency, what will be the skin depth? Then we supposed to use a thickness of the microstrip line as larger than that particular a skin depth value. Okay, means it is again it is based on the operating frequency. What particular line is used for the given particular frequency. So that's why we need to know about the line to be used at what particular frequency. According to that, we need to design the line with a larger thickness or a smaller thickness, because losses can be minimized if the thickness is larger than the skin depth at a given particular frequency there. Then we use this a different kind of a material, okay, because we say that a dielectric constant, that is about it. Generally we say it's about insulating layer or insulating material. So in that particular case here, so we use a substrate in such a way that they have the low losses. Okay, if supposed to be we are using a semiconductor material, okay, or a semiconductor substrate, then in that case the dielectric loss will be a larger there. So consider that what substrate we are using, so that a dielectric losses will be small here. Okay, so everything is depending upon that a thickness value, okay, so of a conductor, what will be the width of the conductor, what will be the height of the substrate there. Okay, so all these losses are dependent on each other there. So then we talk about that first loss, that's about a ohmic loss, or you can say that a conducting loss, that is depending upon the what will be the conductor we have. And generally we say that this loss is occurs if we have the imperfect conductor, or we say that a non perfect conductor. Okay, now what do you mean by this non perfect conductor? Perfect conductor means it has a conductivity, sorry, conductivity value that will be approximately infinite if it is a perfect one, that is infinite value. But if it is a non perfect conductor, then conductivity will be different here. So based on this conducting value for a given particular material or a strip we are using, so according to that, that losses will be increased or decreased there. Because for a given particular line, okay, for a given particular line, it has some particular conductor, and then for a given particular conductor, it has some particular skin depth there. So then again, we need to talk about what will be the thickness of the line and what will be the surface conductor. Okay, again, because for a line, I supposed to draw is supposed to be line now in another way. Now this one is about a strip now. We say this is about it. What will be the height of the strip here? Height of, and what will be the surface here? So based on this particular surface, we say that it has some particular, what we can say that that is about a skin depth. Okay, that is about depth of penetration of a wave. So for a given particular line, for a surface, there will be a surface current distribution. So that's why a current density, okay, what will be the current density because of whatever the surface we are supposed to use here, and for a given particular line, whether that current density is uniform throughout the surface or not. According to that, it has a ohmic loss. And then what will be the thickness about the ground plane? Again, we have the ground plane, the thickness again it is important. Okay, because it has again is that ground plane has a some particular what you can say that a thickness there. So generally, if you consider in terms of the current density, if supposed to be we say that its thickness is very small. Okay, so in that particular case, the current distribution through this particular line will be a uniform here. And in that particular case, generally we say that a small thickness line. So for that particular case, the current distribution is uniform, and then the losses, or we can say that losses in a given line can be write as conducting losses, or you can say that the attenuation here. Okay, is equal depending upon that 8.686 Rs divided by what you can see here, 0 and a W. Okay, so in that case, that W by H ratio, if it is a narrow line, then W by H ratio is less than 1. Okay, if the current distribution is not uniform, then this equation doesn't work. If it is, we can say that if that current distribution is uniform, then this equation works. And this Rs is nothing but what? A surface skin resistance of a strip or a strip line. That is Rs is equal to what? Under root of pi f mu by sigma, or we can write here in another way, that is about a del and a sigma. And that delta is nothing but a skin depth, that is tan delta we have seen earlier. Okay, it's nothing but a skin depth by f mu sigma. Okay, this one is about a skin depth, and we are getting this attenuation here for the uniform current distribution. Then next we see a dielectric loss. Now that a dielectric loss, as we say that conductivity of a dielectric material, okay, because generally it is not a perfect dielectric. If it is a perfect one, the conductivity is zero. For the imperfect dielectric, so then conductivity will not be a zero. And then in that case, conductivity cannot be neglected if it is a imperfect dielectric. So generally, any dielectric material, it has a small conductivity. That's why for a given particular material, a dielectric loss is again depending upon the conductivity there. That is sigma by 2 and a mu and epsilon. Okay, this one is about a dielectric constant. But in the case of what we can say that if we are writing in terms of a loss tangent, okay, then we say that a tan of delta, that is about a loss tangent, is equal to sigma by omega epsilon. If we rewrite the expression in terms of a loss tangent, then it will be what? Omega, okay, sigma by 2 under root of mu epsilon. Instead of that, it will be what? Omega by 2 under root of a mu epsilon and a tan delta. Okay, this one is about the expression. If we write in terms of a tan delta, so right, so that is about a alpha t. So then, if we consider that microstrip line, then microstrip line, because above end is open now, that is in air now. Okay, this that strip is in air now, and then if that region, that strip is in air, then at this constant attenuation value, or we can say that dielectric loss alpha d will be a different here, and that alpha d is depending upon that what will be the effective value of a epsilon r value. Okay, this instead of writing epsilon here, so we need to write in terms of a epsilon r. So in that case, alpha d is equal to 4.34. Okay, is equal to 4.34 q, and there is the factor of epsilon re. Okay, this one a factor, we say that a relative value, or we can say that a effective value for a given particular material. Okay, and again this material has a conductivity into mu 0 by epsilon. Okay, this one is about the equation. Now in that case, if supposed to be this factor, this 4.34 factor, and we need to write what will be the value of this particular epsilon r, we will get the loss. And this particular q is nothing but what? A dielectric filling factor. And that dielectric filling factor. Why dielectric filling factor? Because we say that end is that strip is open now. So that's why Q is equal to what? Effective minus 1 by epsilon r minus 1 will get the Q value. And then we can write, okay, then we can write directly attenuation constant in terms of what? A tangent here, loss tangent, or we can write in terms of a what will be the wavelength there, or we can write in terms of a wavelength here. Okay, so this one is about the expression Q, that's alpha d here. If we write that a factor of this mu 0 and epsilon 0, then this equation becomes a 1.634 into 10 to the power 3 Q sigma under root of a epsilon r. All these values are what? dB per centimeter. Okay, this one. All the value dB per centimeter, all the laws. And we consider that 1 Napier is equal to what? 8.686 dB here. And that Q factor, the dielectric filling factor, it is depending upon that effective value of a dielectric substrate material. Even we can write, okay, this attenuation constant again in terms of a wavelength. So I'll just rewrite the equation again in terms of a wavelength, because all the factors are depending upon that operating frequency of the line. So that's why we need to write the losses in terms of a wavelength. So 27.3 Q, that is the dielectric factor, epsilon r, and a epsilon re. Okay, then tan of theta, lambda g here, that is about a dB by lambda g. This one. Okay, this just like we just say that here. Okay, that is about unit dB by lambda g. That is about the unit here. Okay, so that or we just write this way here, or we say that lambda g is nothing but lambda 0 epsilon r effective, and that lambda 0 is nothing but what? Wavelength in the free space here, or we say that it is about a what? A c by f under root of epsilon r effective. Okay, so this way we can write. This one is about a factor of a guideline. Then next loss is about a irradiation loss, and that radiation loss is depends on the what will be the thickness of the substrate and the dielectric constant. Okay, thickness, substrate thickness and a dielectric constant. So means for a line, this one is about a line, this one is about a strip here. Okay, this one is about a ground plane, and now here we have a substrate. And what will be the thickness of the substrate here? Okay, and what is the value of this epsilon r? So based on that, irradiation losses can be calculated. So generally we say that irradiation losses, I'll just write directly now. It is depending upon that we just talk about the value of that is what will be the thickness, that is h, okay, operating frequency, and f of epsilon re. And this f of re is nothing but the a radiation factor. Okay, this is about it. F of epsilon re is the radiation factor, and it is depending upon that epsilon re minus 1 epsilon re minus epsilon re minus 1 divided by twice of epsilon re under root of epsilon re, and natural logarithm of epsilon re plus 1 and a under root of epsilon re minus 1. This one is about a f of epsilon re. This one is about a radiation factor, and that radiation factor, it will be decreases with the increasing the substrate dielectric constant. That is about the epsilon r value, and through that we'll get the radiation losses. Okay, that's about a RR. And generally we say that this radiation resistance, that is, if you compare with that character impedance there, then if you see that for a given particular line, so what will be the character impedance, and that character impedance which we have some real component of this particular character impedance, and that the small fraction of that real component is nothing but the irradiation loss there. Okay, and then the radiation loss again we say that it is depending upon the character impedance. If that radiation loss decreases, if the character impedance is increases there, and again it is depending upon that a dielectric constant of the substrate there. Okay, if the dielectric constant, if it is a low there, then that case irradiation will be a low here. Again it is depending upon that what will be the impedance here. Then another factor of a line, because since we say that we have the line, and that line has the losses, that is about a conducting losses, then a dielectric losses and radiation losses, then we need to talk about that what will be the quality factor of this transmission line. So then a quality factor, that is about a Q. That quality factor, it is depending upon that what will be the conductor. Okay, again the quality factor is depending upon that what will be the dielectric present there. Means we say that a quality factor of a particular line, it is depending upon the what will be the attenuation, conductor attenuation, as well as the dielectric attenuation. So means we write a quality factor in terms of a conductor attenuation factor is about a 27.3 divided by a alpha c. Okay, that alpha c already we have obtained there for the line there. Okay, so again it is depending upon that what alpha c we say earlier, it is depending upon the a conductivity. So it is depending upon the frequency again. So if we write in terms of a frequency and a conductor, that what you can say that conductivity there. So in that case, the quality factor is equal to a 0.63 h under root of a sigma into f of what will be the operating frequency there. It is about it in terms of a gigahertz. If you consider that a conductivity, if we have a copper strip, okay, that line, if that line has a copper strip, then a conductivity is equal to what? A 5.8 into 10 to the power 7 mho per meter. So in that case, quality factor will be what? 4780 H under root of what will be the operating frequency there. Okay, that is about a quality factor. It is depending upon that a operating frequency. Then different material of a strip, then we have different quality factor, and that depending upon that their conductivity there. Then next about if we use a alumina material, then it has a different conductivity, and then operating frequency, then quality factor again a different here. Now then again a quality factor can be right in terms of a dielectric constant, dielectric attenuation constant. So 27.3 by alpha d. Okay, this one is about a dielectric constant. So if you substitute this value of a alpha d here, then we'll get the quality factor lambda 0 epsilon re into tan of delta here. Then approximately we write tan of a delta here. So this one is about a dielectric constant. Okay, that is the quality factor for the dielectric attenuation constant of a microstrip line. And if you consider that it is approximately is equal to the reciprocal of a dielectric loss tangent. Okay, that is about a tan delta, loss tangent tan delta. And if you see in terms of a frequency, it is a constant with respect to the frequency there. Okay, if you compare the equation there, it is just like a dielectric attenuation quality factor. Okay, so that will be relatively constant at a frequency there. That is about that's all about what we can say that losses we have seen here. Then we talk about the different another kind of a transmission line here. So we have seen today a microstrip line, and then various microstrip line configurations we have seen, and then we have seen a the characteristic impedance of a line. Then we have seen what are the losses of a transmission line. Then another category of a transmission line that is called as a coplanar line. Okay, so in that case, we have earlier learned only a strip line, single strip line. Now we will talk about the a coplanar waveguide or a what you can say that a coplanar transmission line. Okay, so in this case, we have microstrip line only a single conductor. Okay, that is above the substrate, and below there will be a ground. Means if you talk about from the substrate point of view, one side of a substrate it has a ground plane, and another side of a substrate it has a conducting strip. But in this configuration, okay, we say that we'll write here a coplanar line. Okay, this one the about a coplanar line. So in that case, in a coplanar line, if you see that, so it has a central strip line. Okay, one is about one strip here. Particular strip has some width here. That width is supposed to be considered here. Then we have now this one is about a strip central strip here. That strip has some particular width and height. Okay, okay, this one is about a strip now, and then we have a just like we need to see this one again here. This one and this the body of strip. So we say that just like we have got now this one is about a strip, and this one is ground plane, and this one is about your conducting strip. So earlier case, if you see that we have seen that on earlier case we have only this one is a ground plane and this one is the body of strip. So there is no ground plane nearby to this strip. Okay, this one is the open wire and this one is about a ground plane. This one is about a strip conductor. Now in this case, in a coplanar line, we have a strip and that strip is placed or deposited on this particular substrate. Okay, on the substrate both the strips are present. Okay, ground plane is present as well as the strip conductor is present on a substrate. And nearby to the strip, if you see that here is a ground plane. So means this particular strip, earlier in a case of microstrip line, it has only a single ground plane. But in the case of a strip line, it has a two parallel ground plane. And that two parallel ground planes are equidistant from this strip. This distance and this distance is the same here. Okay. And all these ground plane as well as the strip that are present on the substrate here. This one is about your substrate. Okay, this one. This one is about a substrate. For a substrate, it has some particular epsilon r value. And then when we connect a transmission line, okay, so just like we're supposed to consider that when we are connecting a two lines, or in that case we have a ground plane nearby there. So then through that, if we use a strip line, then series configuration is possible, but parallel configuration is not possible. But in the case of a coplanar line, series configuration as well as a parallel configurations are possible using a coplanar line. Again, particular, we say that earlier that microstrip line is that character impedance or their losses both are depending upon the thickness of the strip line. But in the case of a coplanar line, so whatever the substrate thickness we have, okay, or what will be the thickness of this particular strip, okay, they are not means what we can say that line, their character impedance, all other factors are not dependent on the thickness of the substrate there, and we can connect easily, or we can say that a transition from the microstrip to the coplanar line, or we can say that a transition from the microstrip line to a, or we can this microstrip line and this coplanar line, okay, that can be easily connected, or from the coaxial line to the coplanar line, that are easily achievable here. Okay, easily we can connect this particular because separate ground plane here, so they means we can connect these two transmission lines, okay, easily there. So that's why we say that a transition from the microstrip line to the coplanar line is achieved, or it will be very easy here. Then what are the what will be the field distributions here? So earlier we say that we have the strip here. So around the strip there will be a magnetic field line. This one around the strip there will be a magnet because this one is about a strip is propagating. And then in terms of a what you can say that a electric field distribution. Okay, so then electric field distribution is what, because this one is about a strip, it's positive, then this one will be negative. So likewise we have a electric field line. Okay, that is about a field distribution. So if you take a cut section now, okay, if you cut the section of a line, so in that case, what will how it looks like? This one is about your strip conductor, the strip conductor. Okay, so likewise, your line will be looks like this one is about a micro, this one is about a strip. Okay, and this one is about a ground. And this one is about a strip here. So in that case, how your field distributions looks like? This one is about a magnetic field distribution. Okay, and a electric field distributions, if you see that, emanates from the positive and terminate at the negative. Okay, emanate from the positive and terminate at the negative. Means terminate at the ground. So this one is about what you can say that a field distribution, electric field and a magnetic field distribution there. Then a characteristic impedance of a line. Again, the characteristic impedance of this particular coplanar line, it is depending upon that a effective dielectric constant, and again we need to find out what will be the effective dielectric constant for this particular line. So in that case, we use a constant factor k, and that constant factor k is depending upon the values of what will be the line structure is available there. So we can easily calculate that what will be the characteristic impedance of a line, and that characteristic impedance of a line, if you if I supposed to be right here, it is depending upon the factor that is about 30 pi capital K of a K dash here, and that is about the effective value of a material and K of a K dash here. What is the K? K is nothing but what? K, we supposed to be calculate that for a given particular line is nothing but a component, a constant component. And that k component is depending upon the what will be the value of this particular k dash here. Okay. And that is depending upon the what will be the ratio of the slot width and the strip width there. As well as we need to consider that what will be the thickness of the substrate there. Okay, so everything we are supposed to be calculated. That's about it, right? Character impedance. And the losses in the character, the coplanar line, it has only a conductor losses and a dielectric losses. And that losses are again similar to the a microstrip line. So with this, we stop here. Thank you all of you. And again, we say that how that modes are propagating here. So it has a quasi TM wave. Okay, that modes of propagation is possible in a coplanar line. So thank you all of you. Uh, we have learned a coplanar line as well as a microstrip line, their component. So thank you all.